Hello everyone. Today we are going to analyze this beam using Clapeyron's theorem of three moments. Before analyzing, let us see the beam one time. In this beam, there are three spans: span AB, span BC and span CD. In the span AB, we are having point load 24 kN acting on the center. In the span BC, we are having UDL 12 kN per meter acting for the full span. In the span CD, we are having a point load 25 kN acting at 3 meter from the point C. In the point A, there is a fixed support. In the point B, in the point C, and the point D, we are having hinged supports. The moment of inertia for the span AB is 2I, for the span BC it is 1.5I, and for the span CD it is 2I. Length of the span AB is 4 meter, length of the span BC is 3 meter, and length of the span CD is 5 meter. In this beam, there are three moments we have to find. In the point A, we have to find MA. In the point B, we have to find MB. And in the point C, we have to find MC. In the point D, there will be no movement because it is a simply supported end. So, the number of moments to be found is equal to 3. To find out three moments, we need three equations. We can make one equation using two spans. Using the span AB and BC, we can make one equation. And using the span BC and CD, we can make another equation. So we can make only two equations using the available spans. But we need three equations. In the point A, we are having a fixed support. On the left of A, we can make one imaginary span. So, using the imaginary span and the span AB, we can make one more equation. You can see that I have made an imaginary span A0A at a distance of L0. Now, we can make three equations. First, let us take the imaginary span A0A and the span AB and make the first equation. Now, let us calculate the ordinate for AB. In the span AB, a point load 24 kN is acting on the center. If in the simply supported beam, point load is acting on the center, the formula to calculate the maximum bending moment is WL upon 4. Here W is 24, L is equal to 4. After applying in the formula, we are getting 24. Also, when the point load is acting in the simply supported beam, the bending moment diagram will be in the shape of a triangle. For A0A, there will be no ordinate and diagram because it is an imaginary span. Now let us apply the theorem of three moments in spans A0A and AB. In this equation, we have to calculate A1 and X bar right. No need to calculate for the imaginary span because it will be 0. We know that the area formula for a triangle half into breadth into height. Here the breadth is 4, height is 24. After applying in the formula, we are getting 48. This is a symmetrical triangle, so the centroid lies in the center. The distance between the centroid and the right is L by 2. Here L is 4 meter, so 4 upon 2. So for X bar right, we are getting 2 meter. In this equation, let us apply the values. This term will be 0. L0 upon I0 will be 0. Also, this term will be 0 because these are for imaginary span. L1 is equal to 4 meter and I1 is equal to 2I. Also, let us apply the value of A1 and X bar, right? 2I is common on both the sides. So let us take 2I outside and eliminate on both of the sides. After simplifying, we are getting the first equation. Now let us take the spans AB and BC and make the second equation. For the span AB, we have already made the ordinate. In the span BC, UDL is acting for the full span. In the simply supported beam, if the UDL is acting for the full span, the formula for maximum bending moment is WL square upon 8. In this formula, W is 12, L is 3. After applying, we are getting 13.5. We know that if UDL is acting, the bending moment diagram will be in the shape of parabola. Now let us apply the theorem of three moments in the spans AB and BC. Area 1 we have already calculated in the previous step. Let us calculate area 2. Here we are having second degree parabola. The formula for area in the second degree parabola is 2 upon 3 into breadth into height. Here the breadth is 3, height is 13.5. When we apply in the formula, we are getting 27. Both of these diagrams are symmetrical, so the centroid lies in the center. X bar left is equal to 4 upon 2. We will get 2 meter. X bar right is equal to 3 upon 2. We will get 1.5 meter. In this equation, let us apply all of the values. L1 is equal to 4 meter, I1 is equal to 2I, L2 is equal to 3 meter, I2 is equal to 1.5I. Also, let us apply the values of area 1, x bar left, area 2 and x bar right. When we add these two values, we are getting 4 upon I. 4 upon 2, we will get 2. 3 upon 1.5, we will get 2. When we calculate these values, we are getting 72 upon I. When we calculate these values, we are getting 54 upon I. Let us eliminate I on both of the sides because it is common. When we add 72 and 54, we will get 126. Finally, we have made the second equation. Now let us take the spans BC and CD and make the third equation. In the span CD, we are having point load 25 kN. This point load is not acting on the center. The formula for bending moment is WAB upon L. Here W is 25, A is 3, B is 2, L is 5. After applying all of the values, we are getting 30. Now let us apply the theorem of three moments in the spans BC and CD. Area 2 we have already calculated. Let us calculate area 3. It is a triangle. The area formula for a triangle is half into breadth into height. Here the breadth is 5, height is 30. When we apply in the formula, we are getting 75. This is a symmetrical diagram. The centroid lies in the center. So x bar left is equal to 3 upon 2. We will get 1.5 meter. This is unsymmetrical. Let us see the formulas. The centroid distance on the left side is L plus A upon 3. The centroid distance on the right side is L plus B upon 3. We are calculating the centroid on the right side. So the formula is L plus B upon 3. Here L is 5, B is 2. When we apply in the formula, we are getting 7 upon 3. Now in this equation, let us apply the values. L2 is equal to 3, I2 is equal to 1.5i, L3 is equal to 5, and I3 is equal to 2i. Also, let us apply the values of A2, x bar left, A3 and x bar right. MD is 0 because in the point D there is no movement. It is a simply supported end. So this term will be 0. 3 upon 1.5 we will get 2. When we add these two values we will get 4.5. When we calculate this we will get 54. When we calculate this we will get 105. Let us eliminate I on both of the sides because it is common. Finally, we are getting the third equation. Alternatively, we can use the formulas and make the equations. First, let us apply the formulas in the spans A0A and AB. In the span AB, there is a point load. Here we have to calculate 6A x bar right upon L. The formula is WB upon L into L square minus B square. Let us apply the values inside the formula. W is 24, L is 4, B is 2. When we apply in the formula, we are getting 144. Let us apply this value in the equation. Then let us eliminate 2i on both of the sides. Finally, we are making the first equation. Now let us do in the spans AB and BC. In the span AB, we are having a point load. We have to calculate 6A x bar left upon L. The formula is WA upon L into L square minus A square. In the formula, let us apply the values. W is 24, L is 4, A is 2. When we apply all of the values, we are getting 144. In the span BC, we are having UDL. We have to calculate 6A x bar right upon L. The formula is WL cube upon 4. In the formula, let us apply the values. W is 12, L is 3. After applying, we are getting 81. Let us apply these values in the equation. Then let us eliminate I on both of the sides. Finally, we are making the second equation. Now let us do for the spans BC and CD. In the span BC, we are having UDL. We have already seen the formula WL cube upon 4. Here W is 12, L is 3. When we apply in the formula, we are getting 81. In the span CD, we are having a point load. Here we have to calculate 6A x bar right upon L. The formula is WB upon L into L square minus B square. Here W is 25, B is 2, L is 5. When we apply all the values in the formula, we are getting 210. Let us apply these values. Finally, we are making the third equation. We have made three equations. We can apply all of the equations in the calculator and find out the final moments. If you do not know how to solve three equations in the calculator, see the description below. There is a link. You can click the link and watch the video for getting ideas how to solve three equations in the calculator. In this analysis, we have calculated all of the moments. Now we are going to calculate the reactions. For calculating the reactions, we have to split the beam according to the spans. In the span AB, MA will be acting in the anticlockwise direction, MB will be acting in the clockwise direction. In the span BC, MB will be acting in the anticlockwise direction and MC will be acting in the clockwise direction. In the span CD, MC will be acting in the anticlockwise direction. First, let us calculate the reactions in the span AB. In the span AB, there are two moments, MA and MB. In this span, first I am going to calculate RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive, and the distance is 4, so 4 RA. The point load is acting towards the point B in the anticlockwise direction, so it will be negative, and the distance is 2 meter, so minus 24 into 2. Then we are having two movements. This movement is acting in the anticlockwise direction, so it will be negative, and this movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RA, which is equal to 13.37 kN. Now we can easily calculate RB1 by applying the rule summation of vertical forces is equal to 0. In this span, we are having three loads, RA, RB1 and 24 kN. RA and RB1 are acting upwards, so both are positive. 24 kN is acting downwards, so it will be negative. We have already calculated RA, we can apply that. Finally, we are getting RB1 is equal to 10.63 kN. Now, let us take the span BC and find out the reactions. In the span BC, there are two movements, MB, which is acting in the anticlockwise direction, and MC, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive, and the distance is 3 meter, so 3 RB2. The UDL is acting towards the point C in the anticlockwise direction, so it will be negative. For the UDL, we have to multiply with the distance and distance by 2. Here the distance is 3 meter, so 3 into 3 by 2. Then we are having two moments. 8.34 is acting in the anticlockwise direction, so it will be negative. 15.81 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2, which is equal to 15.51 kN. Now, using the rule, we can calculate RC1. RB2 and RC1 are acting upwards, so they will be positive. UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. So 12 into 3, we have already calculated RB2. Let us apply that here. Finally, we are getting RC1 is equal to 20.49 kN. Now, let us calculate the reactions in the span CD. In the span CD, there is only one moment, MC, which is acting in the anticlockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. RC2 is acting towards the point D in the clockwise direction, so it will be positive, and the distance is 5 meter, so 5 RC2. The point load 25 kN is acting towards the point D in the anticlockwise direction, so it will be negative, and the distance is 2 meter, so minus 25 into 2. This movement is acting in the anticlockwise direction, so it will be negative. Finally, we are getting RC2, which is equal to 13.16 kN. Using the rule summation of vertical forces is equal to 0, we can calculate RD. After calculations, we are getting RD, which is equal to 11.84 kilonewton. In the point B and in the point C, we have calculated the reactions two times. For RB, we have to add RB1 and RB2. Finally, we are getting RB. For RC, we have to add RC1 and RC2. After adding, we are getting RC. Now, we are going to draw the shear force diagram. Before drawing the shear force diagram, let us calculate the shear force values. I am going to calculate the values from the point A towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. Using the concept, I have made the calculations. After making the calculations, we can draw the shear force diagram. Now we are going to draw the bending moment diagram. For making the bending moment diagram, first we have to draw the free moment diagram, then end moment diagram, and then we have to combine both of them to make the bending moment diagram. For making the free moment diagram, we have to consider every span as a separate simply supported beam. Then we have to draw these diagrams. In the beginning, we have already seen how to make these ordinates and draw the diagram. Using the end moments, we have to make the end moment diagram. If end moment diagram is negative, it will come above this line. If it is positive, it will come below this line. Right now, all of the values are negative, so all of the three values are coming above the line. Now let us combine the free moment diagram and end moment diagram. Wherever they are acting alone without mingling with one another, we can mark the values with the signs. Wherever they are acting together, we just keep the space empty. Now we are going to end this session. Thank you for watching this video.